So one of the major advantages of Bohr's model of the atom was that it could explain the line spectra of hydrogen. So we had learnt about that, the quantization of the line spectra, in the previous video. In this video, we are going to talk about a few things that I thought was important, but I couldn't, cover it there. So let's start. First one, each transition is associated with a particular wavelength in both absorption as well as emission spectrum. So we know that when you have, technically this is supposed to be in the center and these are supposed to be perfect circles. So according to the Bohr's theory, we have learned that an electron absorbs energy and goes to a higher energy level, and then when it is in its excited state, it emits the energy and comes back to its ground state. And all of this led to the formation of the atomic spectra of hydrogen. So the energy that is equal to the quantum energy difference in between the two energy levels is what strikes the photographic plate. So from this we know that delta E, which is the amount of energy which is absorbed by the electron, equals to E2 minus E1, and this is equal to, so H mu equals to E2 minus E1. So frequency equals to E2 minus E1 by H. And since E2 and E1, first of all, these two are also called as stationary energy. As such, we know that the energy of the orbits is going to be constant. H, that is the Planck's constant, is a constant. All these values in essentiality are constant. So the value of mu will also be a definite value. Okay, so we figured out that the value of mu, that is the frequency, is definite. So, and it is also dependent on the energies of levels of the transition. So frequency is related to wavelength. We know that mu is equals to C by lambda. So C by lambda equals to E2 minus E1 by H, and this can be written as lambda equals to HC by E2 minus E1. Now we know that the values of E2, E1 and H are constant, and C is the velocity of light. So due to this, the transition of the electron from one energy level to another energy level will show the wavelength as a definite value. So the thing was that if there is a definite, we needed to know as to why there is a particular value, and this shows that the wavelength of the line spectra, the specific lines, is unique in nature because of the energy levels. And so this derivation shows that the value of lambda and mu, that is the frequency, and the wavelength are definite in nature. So suppose your electron jumps from the third to the first energy level. This will become E3 minus E1. Okay, so lambda of 3 to 1 will be HC by E3 minus E1. Suppose our electron is jumping from the fourth energy level to the first energy level, HC by E4 minus E1, where 4 and 1 correspond to the energy levels of that particular state. So this is why we get a definite line in our line spectrum of hydrogen. If you've noticed, when we studied about the line spectrum, when it was introduced, if you remember, we had spoken about specific lines being formed. This is because the transitions will lead to the wavelength of the emitted radiation as a definite value. there is the next question. The second question: why are there so many lines in the spectrum of hydrogen? So assume you have only, technically speaking, you just have one atom, right? Why should you get so many? One atom has in one hydrogen. This is because in our sample, you don't just have one atom of hydrogen. It might consist of a large number of atoms. And when it's supplied with energy, these electrons will get excited to various levels. So let's see. Suppose you have, so assume these are the four energy levels: K, L, M and N, where this is the first, second, third and the fourth energy level. Now in our sample, we don't know if the electron got excited to the second or the fourth. Okay, and from the previous question we learned that each of these transition gives rise to emission at a particular wavelength. So the lambda, the value of lambda is specific for each transition. So when these electrons get excited, suppose let's assume it has gotten excited to the fourth energy level, it has to come down. Okay, it can directly come down to the first energy level, or it can come to the second, and then from the second it can come down to the first, or it can come down to the third and then it can come down here, or it can come so there are four cases that can happen. Okay, so assuming that it has excited to the fourth energy level, these are the transition that we think might happen. However, if it is the third, you have various number of transitions happening. If it's the second, it obviously comes back to the first case. Now because of this, you have the formation of various spectral lines because you have a different types of transitions happening. Okay, so in the first part of the video, we learned about the fact that each of these have a specific wavelength because each transition is associated to a particular wavelength, and our sample consists of a lot of hydrogen atoms in it, and each of them might get excited to a different extent. So we might have atoms of hydrogen getting excited to the second excited state, and then it'll just directly come down. If it gets excited to third, it can directly come down to the first, or it can come down to the second and then it comes down to first. So because of this, you have various kinds of lines forming in the spectrum. So from that, so we can understand that Lyman series, if you remember, we talked about all of these, and Lyman series is supposed to be in the ultraviolet region, and Lyman series, I'm so sorry, it's Lyman series. Lyman series goes from second, so n can be equal to 2, 3 and 4 and 5 and so on, to n equals to 1. So basically it's going from the second, third, fourth or fifth energy level to the first energy level. Balmer series is formed because n equals to 3, 4, 5 and so on to n equals to 2. If you remember, we learnt all of this in our Rydberg equation as well. We studied about the fact that the values of n1, n1 and n2, and we studied about the values of n also. So this again, so that is in relation to this Paschen series, n equals to 4, 5 and so on to n equals to 3, and bracket n equals to 5, 6 or 7 and comes back to n equals to 4, and fund n equals to 6, 7, 8 to n equals to 5. So they are basically coming back to their respective various number of energy levels. So our Balmer series is the only one which is observed in the visible region. These three are observed in IR, and this is observed in the UV region. And this is with respect to the transition. Basically, suppose you have 0, 1, 2, 3, 4, 5, 6, 7, assume. So 1, 2, 3, 4, 5, 6, 7. Your Lyman series will be observed from 2, 3 and 4 coming down to shell number 1. So these transitions. Your Balmer is from 3 to 2. So as you can see, basically we are talking about higher energy to the lower energy levels. So with this we finish the Bohr's model for the line spectra of hydrogen. If you haven't understood the basics, you have to do check out the initial concept of atomic spectra and the discussion on the line spectra of hydrogen, because that will help you better. In the next video, I believe we will be discussing about the limitations of Bohr's atomic model.